Yeah,
Yes.
okay. I started it now.
Yeah, I've started sharing my screen, but maybe it's a bit early. Yeah, thanks Andrew for setting up the whole system.
Yeah, I was talking about Yu Yang is here. It's coming. Well, I guess we should be starting next year. I guess we're gonna start and you like.
Oh, sorry, what did you say? I should start?
Start actually.
Okay, great. Okay, let me can you see the screen?
Yeah.
Yeah.
Okay, nice.
Yes.
Cool. Yeah, okay, so I'm going to talk about normalizing flows and manifolds. So basically different ways of parameterizing and learning property distribution on Riemannian manifold. So I think I've made too many slides. I'm gonna skip a few, and also, but yeah, feel free to like interrupt, if you have questions or remarks. I try to not put too many questions and more use like pictures, but I guess there's like quite some questions. But yeah, basically feel free to like ask questions. I guess this is what's interesting is that I guess the discussion that it creates. So yeah, first of all, sorry, what?
On that speaker view, is that what you meant to do? Or do you want it on the original slide?
We can see your notes basically.
We see your speaker notes here instead of the kind of slide.
Sorry, what should I? Oh, you see the speaker notes. Oh wow, sorry.
We know
rookie,
all your dirty secrets now.
Rookie mistake. Does it work? No.
Yeah, it's fine.
Can you see that? And the speaker notes?
Yeah.
Okay, great. Sorry. Yeah. So what is the task, and why do we care about that? So I guess there's different tasks that people may care. One is jointly learning the manifold and a density on the manifold. So there's like quite a line of work on that regard, on that. Yeah, on that. But where we're gonna focus is assuming that we're like giving a manifold and then parameterizing and learning a property density on that manifold. And so I think Anthony may be presenting. I mean, he's been working on that, and maybe he's gonna present something next week. I don't know. And so yeah, today.
I said Anthony will be giving a talk next Tuesday, actually.
Next Tuesday, okay.
And we have an unusual time because he cannot make it another day. He's going back to Canada. So, yeah.
So yeah, this is Anthony, and that's what he's going to talk about, I think, on Tuesday. And so this is me, and so this is what we're going to talk today. Yeah, so very briefly, so we are basically assuming that we're given a Riemannian manifold. So I'm going to kind of assume that people have like basic knowledge of Riemannian geometry. If not, like please interrupt. I guess there is no need to know everything, but okay. So we have like a manifold and like a metric, and so I guess I'm just gonna mention this and then won't mention it again. But basically, the metric, the Riemannian metric is inducing like a change of volume, and so we have a new kind of Riemannian measure instead of the Lebesgue one. And so what we care about is basically densities with respect to this Riemannian measure instead of with respect to the Lebesgue one. But so I guess we're like assuming that the measures that we care about have a density, and so we can just like care about the densities. And so we are assuming that this density has like support on the manifold, right? That's the assumption. And so then the goal is to like parameterize a distribution p theta. So could be parameterized as this. So that's kind of the definition of a normalizing flow with like a base distribution. And then we push forward that base distribution along some kind of map, some kind of flow. But I'm gonna talk a bit more about that later. And then the idea is to just learn the parameters of that parametric distribution in order to minimize some divergence or distance between the data target distribution and the parametric one. So wait, why do we care about that? So to be honest, in the literature so far, I feel like most of the applications are kind of toy-ish, but I think it is like nonetheless quite interesting because in terms of Earth and climate sciences, you can assume that like the Earth is spherical, and then you may want to learn like two-variational inference or density estimation on that. In robotics or virtual reality, I guess you have the SO3 Lie group that appears quite often. In computer vision, you can have like the symmetric positive definite matrices are also SO3. And also, in like lots of physics that I'm not sure I do understand everything. I mean, I'm quite sure that I don't. You have like SUN and other kind of fancier Lie groups that appears. And so, you may want to have a marginal inference on this group, on these manifolds, because I don't know, you have like a latent space that is assumed to be SO3, for instance, or you may want to just like fit a distribution to your data that lives on the sphere. Anyway, so that's for the motivation. So a quick recap of what are normalizing flows, in case not everyone is familiar, but I'll go quite fast. But so I guess in one sentence, there are diffeomorphism with tractable log determinant Jacobian. And so that is the slide. The idea is to, in order to parameterize a flexible property distribution, one would start with like a simple base distribution, such as like a Gaussian here, and then construct a flow, which could be the composition of several simpler flows, and then basically that's it. You would define your model distribution as the push forward of your base along this flow, which is written here with this symbol here, the push forward. And in terms of sampling, that means this, right? You sample Z0 from your base distribution, and then you evaluate your flow, and that gives you a sample from your parametric distribution. And then applying the change variable, you can compute the density of your of samples from your parametric distribution by computing the density of the base distribution and this determinant of the Jacobian. And so I guess the key is that this is just in general hard to compute, and so the idea of all these class of models is like to design flows so that this is easy to compute. But I guess there's a trade-off between this being easy to compute and the expressiveness of your flow, and hence the expressiveness of your class of probability distribution. So that's like for Euclidean normalizing flows on like Euclidean spaces. I mean, it's for like generic spaces, I guess. And okay, so now I'm gonna go through, try to like present different approaches, how to parameterize the flow for like manifolds, density estimation. And so, so I'll go through different approaches and try to like cite like existing papers from the literature. So hopefully that will give you a kind of like good overview of the literature on normalizing flows for manifold. So I guess, first, the most obvious thing is to build a global map from a Euclidean space, to a manifold. And then one can think of parameterizing a normalizing flow on RD, and then to kind of like project that on the manifold. I guess the issue is that just by definition, there does not exist any such map that is invertible. Otherwise, the manifold would be flat, would be like isomorphic to RD. So which means that either such a map is like non-injective or non-surjective. And so here, let's see an example of like lack of surjectivity. If we take the example of the sphere and take this map to be the inverse of the stereographic projection. So here I've just reminded you with like a small drawing what is the stereographic projection. So if we take the projection with respect to the North Pole, then a point Z1 here would be projected here and Z2 a bit further. And basically, the closer you get to the North Pole, the further away you get from the center of this 2D plane on which the sphere is being projected. So the North Pole has no image. And so the idea then would be to start with like a simple Gaussian 2D Gaussian distribution on the plane, and then to apply a standard Euclidean normalizing flow on that, and then to project this back onto the sphere with the inverse stereographic projection. And so I guess the flow here would be defined as the composition of this like standard normalizing flow on the 2D plane and the inverse stereographic map. And there you have a parametric distribution on the sphere. But because of the like subjectivity, as I've said, basically, if you have mass close to the North Pole that you want to model, it means that in the 2D plane, you need mass like close to infinity. So we can feel like numerically, this is going to be challenging. And I guess also topologically, since this cannot be a diffeomorphism, it means that you're like losing the topology of your manifold in a way, right? But I guess numerical challenge maybe are the biggest issue with such methods. So this was proposed in this paper over there. Another such map, instead of like the inverse stereographic map, which is quite generic, is the exponential map. So here it's written for like manifold, because the tangent spaces are like isomorphic to RD, or here it's written for like Lie groups. And but it's the same idea. It's just like you define a normalizing flow on the Lie algebra or on the tangent space that is isomorphic to RD, and then you apply the exponential map on that. And then you can compute the likelihood. The issue is that, so I guess the exponential map is not always subjective, but and for like simple case, I mean for like standard Lie groups, it is often, but it is definitely non-injective for like compact spaces. Like, and so the issue is that if you want to evaluate the likelihood, you have to sum over all the pre-images, which can be like an infinite sum. And also, this Jacobian term is not always, I guess, in general, is like how to compute for simple groups like SO3 or SO2. You can like easily compute that closed form. Yes, so I guess this is kind of another inconvenience, the lack of injectivity, right? Because you have this infinite series here that appears. And yeah, I guess that was proposed in this paper. I guess we do something similar in our paper. Okay, so that was like the use of a global map, but why not have like a collection of local maps? And so these are basically like charts for those who are familiar with the Riemannian geometry. So I guess that's how one define a smooth manifold. It is by having a collection of charts called an atlas. Okay, and so these charts are like an open set in the manifold and a homeomorphism that maps this open set to an open set of all D, with D being the dimensionality of the manifold. And and so you need a covering of your manifold, so a collection of charts so that the union would cover the entire manifold. And then I guess FYI, like a smooth manifold, I mean, a manifold is smooth when this transition map to go from one chart to another in a way are smooth. Anyway, and so, but I guess instead of having one global map, one can think of having like basically, a collection of such local diffeomorphism between the manifold and RD, and then having some kind of like mixture distribution. Anyway, I won't go into detail, but I guess that then you don't have the issue of the lack of injectivity or subjectivity, but then the issue is that you still having like a mixture, you still have to sum over all the components. and compute the Jacobian for each term. Anyway, and so this is like vaguely the idea followed by this paper. Okay, so am I going too fast or too slow? I don't know. So now another class of method are continuous normalizing flows, which are based on parameterizing the flow as the solution of an ODE. So if you consider I guess a curve parameterized by time zt that lives on your manifold, and then you define his temporal derivative to be equal to this thing, which is a vector field that defines an ordinary differential equation. So a vector field is basically a map that takes like a point from your manifold, maybe some time components, and then outputs a tangent vector. And so then one can solve for this ODE. So intuitively, you kind of like follow that vector field along time for some time t, and then you get a new point that still lies on your manifold. And so you can do that for like every point on your manifold, and you get like a new point. And so the flow can be seen as like a map from the manifold given some time that gives you a new point in the manifold and this solved for the ODE. And so I guess this like time component is a bit arbitrary. We can just fix it to be like some capital T, and then the flow is a map from the manifold into itself. And so then we can just use this map, this flow, the solution of the ODE, as the flow that we want to push forward or base measure to parameterize our distribution. So I guess then in practice the question is like, how do you solve the ODE? But that works pretty well if you see the manifold as being embedded in a Euclidean space. And then also the question is like, is the flow a diffeomorphism? And basically we show in our paper, this one, that like for compact manifolds, it is a diffeomorphism. So smooth and bijective. Okay, and so since we care about density estimation, then we care about it being able to evaluate the likelihood of our parametric probability density. And so I guess similarly to the neural ODE and field papers, we leverage the time contingency of the flow to express the change of log density as being the minus the divergence of the vector field. So this is just the continuity equation, or I guess can be seen as a Fokker-Planck or the Kolmogorov-Ford equation without the diffusion coefficient. And so then one can integrate this over the trajectory to get the new density. So I guess this in practice will be approximated, right, given the different steps written by your ODE solver. And then so there's still the question about how do we parameterize the vector field and how do we compute its divergence? And so then there's like different ways to do that. So one way is to choose like I guess a local chart, local coordinates, and to express the vector field with respect to what's called the coordinates vector fields here. So for this sphere is this like E theta, E phi vectors that people are familiar with. And so then one can parameterize the coefficients with the neural network. So the weights of that decomposition are parameterized with the neural network. And so then we, that yield a vector field with some learnable weights theta. And so with the choice of local coordinates, then one can compute the divergence with this formula. So in the Euclidean setting, you don't have these G terms that are the metric tensors, and so you do recover the trace, right, of the Jacobian. You sum over all the partial derivatives. And so in practice, if the manifold dimensionality is big, computing this Jacobian is tricky, but you can use like stochastic estimators to do that by writing this as like the trace of a matrix. Similarly for the similar as the field paper. Another approach is to decompose the vector field on a noise basis that, I mean, it's not a basis, but basically a collection of vector fields that span the tangent space. So they generate the tangent space, which is what we care about. And also they have like zero divergence. And these basically exist for any homogeneous space, and they are given by this formula. So I guess intuitively they are the vector field induced by the isometry of the space. So here for like, I guess for S2, they are the vector field that generates the rotation around the three axes. And the fact that they have this property means that if you compute, and then I guess we similarly we just like express our vector field as like a decomposition on this collection, and we parameterize these with like a neural network. And so then the divergence is nice because you basically get two terms, and one of them is zero because of this property. And so you have this term, which is still tricky to compute for like large dimensions, but you can also use a stochastic estimator. Yeah, that was proposed in this paper. And so another approach that was proposed in this other paper is to still with like a neural ODE approach, is basically to, I mean, I guess to use the definition of a smooth manifold and to rewrite the ODE from the manifold onto charts. And so one can, I guess if one has a vector field on the manifold and a collection of charts, then one can like pull this back as a vector field on the open Euclidean space, and then and then re-express this ODE basically on each individual open sets that is given by the charts. And then the idea is just that then there is no ODE solved on the manifold anymore, but the ODEs can be solved on Euclidean spaces. And I guess since there is no like global chart that would cover the entire manifold, right? Otherwise it would be Euclidean space. You need to do that on each individual chart and kind of like make sure that you connect things properly, which I guess can be summarized by here. First, you start by pulling this here onto the first chart, then you solve it on the first chart. Then when you kind of like exiting that, you go into the second one, and so on. And then the likelihood can be computed. Basically, you have the log the Jacobian that comes from the pulling and pushing from the charts, and then you have the terms that come from like the ODE solver on on each individual chart. So I guess this kind of like in a way leverages the definition of smooth manifold, and instead of solving the ODE on the manifold, like solve it in the charts. I mean, in the open space defined by the charts. Does anyone have like any question on this? I feel like I've been going maybe a bit too fast.
Hey, can I ask a question maybe?
Yeah.
So essentially, you're building the sort of the original measure on RD, and you're pushing it forward rather than using a global map, using the charts and the ODE. Is that correct?
Yes. Yeah. I think this is correct.
So does that mean that let's say that for every different chart in the atlas, you're trying to map it to a different open set in RD?
Yes, I guess so.
So you're trying to, because if you've got have you got a single prior on RD, or have you got multiple, one for each chart?
No, sorry. So I don't think you have any prior on RD. No, so the prior is still on the manifold.
Okay. So you're not mapping a distribution from RD to the manifold. You're just evolving the distribution of the manifold. Okay, all right.
No, you're right. Yeah, that's exactly. You basically yeah, is similar to the previous approaches, right? It's just that instead of solving the OD and the manifold, you're basically using your collection of charts or so things
to solve it in
on the
RD.
chart. Yes,
Okay.
yes.
Okay.
So that then you don't have to, yeah, that's exactly it.
Okay.
Yeah, but if you have like a sphere, you would start with like a uniform prior on the sphere. Sample a point, you'd be this like first Z0, and then yeah, pull it back on the first chart, solve your D here, and so on. So yeah, so these were like continuous normalizing flows based on neural ODs. And so another class of methods are flows defined via the exponential map of a convex potential. And so from those who are familiar with optimal transport, that's kind of maybe obvious or at least makes sense. And so I guess this theorem 9 by Mike from this paper that shows that there exists a unique map from the manifold onto itself, such that basically yeah, so that's what we want, right? So that basically the push forward of the base distribution yield the target distribution, and also so that it minimizes this cost, right, which is familiar for OT people. I'm not sure how familiar people are, but okay, I assume that people are. And so here the cost, I miss half, is half of the geodesic distance. I mean, I guess the half doesn't really matter here, but it will later. And so, yeah, that means that not only this map is parameterizing, I mean, is basically targeting the right probability distribution, but also it is optimal in this like transport cost sense. And also what's nice is that map has like an expression, and it is given by the exponential map of a convex potential. And so here, I guess convexity on manifold is defined as like C convexity, C being half of the square root of the geodesic distance. And so C convex functions are written as this, the infimum of Y being on the manifold of the cost. And yeah, and some like dual potential. And so basically, if we and then that's it. We can basically sample points from the base distribution and then apply that flow, one or several times, and that gets us new samples. So here's like a small drawing, and so I guess the question is like how to parameterize, because basically this is it, right? If we can parameterize all the C convex functions on that manifold, then basically we can express all optimal transports. That gets us our target distribution back. But I mean, as you can see here, it's like a bit tricky to parameterize the C convex functions. So, and so then the likelihood, so often it's just easier to basically work in terms of coordinates in the ambient space. If you think of like S1, you would work in R2 just in terms of like coordinates and parameterization of things. And so to compute the likelihood, then you would see F as like a map from R2 to R2. And so Ethan then will just form like an orthogonal basis of the vectors tangent to the manifold at Z. And so that's your change of a variable formula. Basically, if everything is like Euclidean, then you just get the normal formula. Anyway, and so sorry, what?
What is E? I didn't hear.
E forms an orthonormal basis of vectors tangent to the manifold at Z. So it basically projects R2 vectors onto the tangent space at Z. I don't know if you. So it's like, you can. I guess you can see it as like a projection of vectors in R2 onto this tangent space, for instance, at Z. So like a horizontal vector here. And that's just basically because it's more convenient in practice to parameterize, if you care about distribution on S1, to parameterize everything in like with R2 coordinates, with like Cartesian coordinates. If you implement the thing in practice, you're not gonna use like you're gonna use like X, Y, even though your points will satisfy like the circle constraint, but in terms of like implementation, everything is like functions of R2 to R2. But I guess that's why you need this E term for the change of density to make sense. I don't know if that. I guess Anthony is going to talk more about that Tuesday. Yeah, does it kind of make sense? Not really.
Yes, okay.
Okay. Yeah, so then the question is how to parameterize this class of C concave potentials, and so there's like different papers on that. So I guess one thing which is nice on like spheres and products of spheres is that the space of such C concave function convex functions is a convex space. So then you can just have like you can have like more expressivity, increased expressivity by having a convex sum of like simpler C convex potentials. And so these two papers basically propose to parameterize these simpler potentials as like a function of the geodesic existence, and such that they satisfy this. And if that's the case, then this is indeed like a C convex potential. And so then there's just different proposition to how to parameterize that. So this second paper proposes this it's like high frequency way, and the first paper here proposes this one that's like a bit reminiscent of like radial flow. So I guess the learning, the things that are being learned here are like these new I's and the betas. So I guess this is like there's nothing new right here. You have some parameters, but like not that many. But that's one way to parameterize C convex functions. Another way is proposed in this paper, Riemannian convex potential maps, is to basically have like to parameterize it as like a piecewise quadratic potential. So I guess the drawing here helps. So they have a collection of yi's and alpha i's, and so the yi's are kind of the anchor points of the minimum of these quadratic functions, and the alpha i's are the height. And so then the potential is defined as this. And so so that's the dual potential, and so the potential, which is like defined with this formula, is given by this. And so what's nice is that then the flow can easily, so the flow is that the exponential map of minus the gradient of your C concave potential. And basically everything is easy to compute and tractable because of their choice of parameterization. I guess that comes at the cost of like expressivity, of course. And so that's what the next paper is trying to remedy: implicit Riemannian concave potential maps. They basically parameterize, basically, if we look at the definition of C convexity or C concavity, they parameterize this dual potential with a normal network. I guess the issue then is that this is implicit. You can't solve that closed form because you need to solve this like minimization problem. Basically, each time you want to evaluate your potential. So here, if we write with y star the solution over that minimization problem, then it is given by that. And so basically what they look at this paper is like constraints on this neural dual potential phi theta, so that if you apply stochastic, gradient descent or stochastic gradient descent, the minimum that you find is the global minimum defined here. And so if you have like some kind of Lipschitz constraints on the gradient and the Hessian, basically that works. That's what they show. But it's still a bit tricky because you don't really care about the potentiality, but about its gradient, right? Because you want to compute the exponential map of that gradient. And so you still have this term here. So which means that you're gonna have to differentiate with respect to the minimizers, but it can still be done via the implicit function theorem. Anyway, I guess in this paper they have quite, a big chunk of this paper is basically how to compute the derivative that you care about to be able to train your model. Okay, maybe I want to a bit fast, but we can come back later to things that if people are interested in. And so I guess another class of methods which are quite famous, right, is like score-based diffusion, denoising diffusion models. So I think most people are familiar with that, but just in case. So the idea is to construct a diffusion process, so that if we start with some kind of like a data distribution and we apply this diffusion process, then after like I guess an infinite time, we get the invariant measure. I mean the measure that is invariant with respect to that diffusion process. And which means that basically if we were to start from that invariant measure, let's say it is simple to sample from that distribution, then it'd be nice to like be able to reverse that to get data points from the data distribution. And so what's nice is that there's this result that shows that there exists a reverse SD that is also a diffusion process. And the only difference is this new term here in the drift. Yes, and so I guess here the flow is this is stochastic. But then the idea is like you sample from this invariant measure, and then you simulate the diffusion process, and then you get a new data point. And you can also evaluate the density because there exists an OD that is associated with this diffusion process, and that gives the same push forward. And so basically one can do the same thing on Manifold. So that doesn't exist, but it's basically Arnaud, James, Valentin, and Michael and I, and I guess other people also are starting to work on that. And so the idea is if we consider compact manifold, then if we choose the diffusion process to be a Brownian motion, then the invariant measure would be the uniform measure. And and then by sampling this uniform measure and then simulating the reverse diffusion process that is associated with a simple Brownian motion, then one can sample data points that are distributed accordingly to the data distribution. And I guess there's like in these models you can't actually compute this Stein score. You need to like estimate it, usually with like a neural network. And so here it is similar. And so this is a vector field, right, that takes input data points from your manifold and outputs a tangent vector. So basically it's a bit similar like algorithmically to this continuous normalizing flow where you need to parameterize a vector field and learn it. So these were kind of like different approaches, different perspective on like how to parameterize flows on manifolds. And so I guess there's always kind of trade-offs and theoretical questions like, is the flow bijective? Is it smooth? What is the expressivity of the flow? And I guess what we care about is more like the expressivity of the push forward. And so is this a kind of like universal approximation results? And also like crucially, what is the computational complexity of sampling? But I guess what's usually hard is more like evaluating the density because of this log determinant Jacobian term. And so those methods are usually like trade-off between like expressivity and computational complexity, and especially like how does that scale with respect to the dimensionality of the manifold. So that's pretty much it. Thanks. Thanks for listening.
So in your experience, Emile, I mean, I guess you tried a few things because you worked on that during your thesis. So what was the kind of the best?
Most one? The best approach?
Yeah.
I don't know. I guess also one of the criterion that I didn't write is like, I guess how easy it is to implement, right? That's something people care about. I guess maybe one of the easiest way is just that with like the exponential map or something like this, because it's just like if you can compute close form the log depth of the exponential map, and that's basically like very easy to implement. So, and that can be like expressive enough. I haven't really like played with this potential this kind of like exponential map of like a convex potential. I feel at least these two approaches are like not expressive enough. Obviously, this one also, I mean, if you look at basically what is the map, it's just like it gets you to the closest y. So and so this is like way more expressive, but I mean, it looks like quite complex, the density evaluation. I don't know, so I haven't like implemented or like played with it, but it's definitely non-trivial.
The literature constraints on the potential, because I guess for certain manifolds it's quite trivial, but for, I guess in the paper they only use spheres and stuff. I think what happens if it's not manifold?
Sorry, I'm not sure I heard everything very well.
But you were talking about the implicit layers paper.
Yeah.
You have this constraints on the potential or on the map, right, or bounded. I guess this links to the expressiveness of the network, but also links to that we find for certain manifolds, but not for others. How restrictive is this? Is it fairly common assumption, or is it quite? I don't know how restrictive.
Yeah, that's a good question. So I guess there's two things, like how do you constrain that in practice, right? From what I'm aware, like it's you can't like very easily like constrain the Lipschitz constant, right? You need to like estimate. I don't know. Usually it's like some kind of estimated lower bound or upper bound on these things. So there's that. I don't think it's very easy, and I don't think you lose a lot because I don't know. It would be I feel like intuitively, I don't think you lose a lot. It would be nice kind of like show results of like how much you lose or whether you lose anything. Maybe in the theorem. Sorry, what?
But it was a very simple examples that we use in the paper. I was wondering if there's more complex examples of manifolds. I don't know. I guess people normally just use spheres.
Yes, in this paper, I think they mostly focus on like spheres and products of spheres like Tori and this kind of thing. So you're asking whether there's more complex examples than that?
Yeah. Do the other papers you consider look at more complex examples?
Yeah, I'm sorry, I can't hear that well.
Sorry, the other papers you considered in your presentation, they consider other more complex manifolds other than spheres.
I guess in our paper we consider like the hyperbolic space, but it's not like very complex. I guess those are like constant curvature manifolds. This one by Fallacy and Ferry like considered was mostly focused on Lie groups. So I think they had like SUN, SON, this kind of things. Yes. Yeah.
Okay, thank you.
And to finish answering like Arno's question, otherwise I think like the continuous normalizing flow approach is nice, but definitely like I guess the ODE solving is quite a computational a bit bottleneck. So it depends like how much in a hurry you are. But otherwise I don't know, maybe I'm a bit biased, but I feel it is like a good approach. I don't know, I'm not very convinced yet by this convex potential maps.
Emile, For a project, when you're discretizing the ODE, are you leaving the manifold? Do you have problem you have to reproject at each time step, or it's okay?
Yeah, so in practice, I guess theoretically, yes, you need to project it each time. I mean, if you're indeed like so, which is what you're doing, like solving in the ambient space. And I guess like theoretically, if you just solve it perfectly right, then your solution lies on the manifold. But if you use like an adaptive solver, then basically your error would be small enough so that in practice we only need to project like at the end, so around here. You don't really need to project like each time. I don't know, maybe because our manifold was like simple enough, but on the sphere at least that was the case. And so, and I guess like also projecting on the sphere is very easy. I guess it is trickier if you want to project like on a, I don't know, SON, then that's like a bit more computationally intensive. But if you do it only once, that's like perfectly fine. So yeah, basically, I guess my short answer is that I feel like the ODE solving and making sure that your numerical solution still lies in the manifold is like actually not an issue. Yeah, basically, I tried quite some different things before, constraining the solution to be in the manifold, and then I just like try basically just the Euclidean setting and yeah, projecting, and that worked perfectly.
Is there any other question? No? Well, thanks, Emile. We're gonna have lunch downstairs in about 10 minutes, so everybody's welcome.
Okay, I'm stopping the recording.
Yeah.
Thanks, George.